Okay, today we're going to talk about conditional statements and biconditional statements. Let me start by writing a statement here, okay? If an integer, but let me say it this way. If the integer a is a multiple of 6, comma, then a is divisible by 2. Let me shrink this down. I don't want to go off the screen. Okay, there we go. Okay, look at that statement. If the integer a is a multiple of 6, then a is divisible by 2. You see these two words here, if and then? Okay, when you see that, what you have is a kind of statement that's called a conditional statement or an implication. All right? Conditional statement is what those are called. Also known as an implication. Because being a multiple of 6 implies that you are divisible by 2. Okay? The key words are if, then. Now, let me show you the symbol for this. There's one symbol that means if, then, or implies. Okay, let's talk about this. So, I want to point out something to you. This is a statement by itself right here. Let me make this pen bigger here. That's a statement by itself, right? The integer a is a multiple of 6. Well, it's an open sentence, right? Because it depends upon what a is. So we could call that, I'm not sure if I used the word open sentence in this class or not. I have another class called Discrete Structures that studies the exact same material but in a different order. So sometimes I might say a word here as though we've used it before, and really we haven't. That means that I used it in my Discrete Structures class, and I thought that I had used it with you. And I'm not sure about the term open statement, or rather open sentence. So let me cover that really quickly just in case we haven't. I want to review a couple things. What does the word statement mean? Statement is a sentence that's true or false. Okay? An open sentence is not a statement because it has a variable in it. So it's neither true nor false, like this one that I underlined in blue. The integer a is a multiple of 6. That's neither true nor false. It all depends upon what a is standing for. Once I plug in an actual number for a, then the open sentence becomes a statement. If I plug in the number 12, then it would be true. The integer 12 is a multiple of 6. If I plug in the number 9, it would be false. Okay, that's called an open sentence. I'm going to call that P of A. The book is just calling it P on page 42. Which is fine, but for open sentences, it's good to call it something like P of A, because the truth or falsity depends upon A and what number you plug in for A. Okay? Now, this is another open sentence. A is divisible by 2. That might be true or false depending upon what you plug in for A. Let's call that one Q of A. All right. Now, if I put those two open sentences together, into the open sentence, if the integer A is a multiple of 6, then A is divisible by 2. Well, actually, that's no longer open. That is an actual statement. It is true or false. Okay? It is talking about the relationship between P and Q. So we could call that, well, the book calls it R. But I'm not going to do that because I'm going to show you what is the symbol for a conditional statement. Here's the symbol. You go P of A, and then this type of an arrow, which is called a double arrow, and then Q of A. When you see this symbol right here, that is the symbol for, whoops, that's the symbol for implies, or if then. But we don't say P if then Q. That doesn't make sense. We would say if P then Q, or P implies Q. Okay? Now, let's do a new example. Here's one that I like to use all the time with students. If my car is out of gas, then my car won't run. Okay? So I'm going to write, my car is out of gas. Now that might be true or not. But it's definitely one of those two. It is true or it's false. And I could tell by going out and checking my gas gauge. Okay, so the fact that that is either true or false means that that is a statement. So I'm going to call that P. Okay? Now, here's another statement. My car won't run. That might be true and it might be false, but it's definitely one of those two. And I could find out which one it is by going out and trying to start up my car. And then I would find out if this statement is true or not. I'm going to call that statement Q. Okay? So now, P implies Q would look like this. If my car is out of gas, then my car won't run. That is a statement. I put two statements together into one big statement. Okay, and this first one is called the hypothesis. And the second one is called the conclusion. Okay? Now, let's talk about truth and falsity. All right, so this one up here. My car is out of gas. Is that true or false? Well, the answer is you don't know, right? You'd have to come to my house and check in order to find out if it's true or false. You don't know. What about this one? My car won't run. Is that true or false? Same situation. You don't know. You'd have to come and check. But they're both statements, so they are either true or false. P might be false, and Q might be true, or maybe vice versa. I don't know. Okay? Now, look at this statement. If my car is out of gas, then it won't run. Is that true or false? Or here's an even deeper question. Do you need to know whether P and Q are true or false in order to decide if this implication is true or false? I think not. What I'm saying is this. I think that the implication is true, even if P might be false. You see what I'm saying? P says my car is out of gas. That might be false. Maybe my car has gas in it. Then P would be false. But P implies Q, I think we can agree would still be true, right? Oh, I should point out, I don't own a Tesla or something like that. Okay, I own a gasoline vehicle, so that's important for me to say, I suppose. Because I don't want somebody to say, well, if you have an electric car, then it could not have gas in it and it will still run. Okay, so let's count out that possibility. Can we all agree that a gasoline-powered vehicle, if it's out of gas, then it won't run, right? So that tells us some very important information, that the truth of P implies Q does not depend upon P being true or false, and it does not depend upon Q being true or false, but it does depend upon the relationship between P and Q being true or false. Okay, it doesn't depend on each individual statement P and Q. It only depends upon their relationship. How do we indicate that? Well, I showed you in the previous lecture. We do it by making a truth table. Okay, let me show you again how a truth table works. So what I'm going to do is draw a table here. We did truth tables for conjunctions and disjunctions, so we've seen this before. Okay, my variables are P and Q. Let's write down the possible combinations. We might have P true and Q true. We might have P true and Q false. We might have P false and Q true. And we might have P false and Q false. Okay? And it's that combination of the two that will tell us whether or not P implies Q is true or false. Okay? And here's how it works. If P and Q are both true, then the implication P implies Q is true. If P is true and Q is false, then the implication P implies Q is false. And if P is false, then the implication is true. It doesn't matter whether Q is true or false. You're going to need to have this truth table memorized. Okay? It's easy to memorize, very easy, because look at it. What's the only thing you need to know? I'm going to write this down. For implications, the only time an implication, or let's say let's use the word conditional, is false is when the hypothesis is true and the conclusion is false. That's the only time a conditional is false. In all other cases, it's true. Okay? So let me explain to you where we're coming up with these truth values from. Okay? So let's write P is the statement I ate breakfast. And Q will be the statement I am full of energy. Okay? Or let's make it a little bit more specific. Let's say I can run 5 miles. Now, do we agree that those are both statements? Think about that. Are they both either true or false? They are, right? Either I ate breakfast or I didn't. That's either true or false. Either I can run 5 miles or I can't. That's either true or false. So those are both statements. Okay, now let's look at this possibility. P and Q are both true. So what would that mean? That would mean I did eat breakfast, and it also means I can run 5 miles. So I want you to pretend that you are going to try to disprove this statement. Okay? We're going to do this sort of through the back door. Okay? Instead of convincing you that that statement's true in this case, what I'm going to do is convince you that it's not false. Okay? So, here's the statement we are testing. If I ate breakfast, then I can run 5 miles. Okay? And you come over to my house and you see me eat breakfast. So that means that P is true. And then you see me go out and run 5 miles. So that means Q is true. Could you possibly claim in a court of law that you have any evidence at all to disprove that statement? If you said, well, I think that's a lie, right? Could you convince anybody that that's a lie? No, you would have nothing to go off of, right? Nothing at all. No evidence that that's false. After all, you saw me eat breakfast and you saw me run 5 miles. Now, is it the breakfast that allowed me to run 5 miles? Well, that we do not know, because maybe I can run 5 miles on an empty stomach as well. But the point is, you don't know if it's the breakfast that allowed me to run 5 miles, but you certainly have no evidence to say that it wasn't. So therefore, you cannot claim that that green sentence is a lie. And every statement is either true or false. And so if you can't claim it's false, then it must be true. Okay? And that's why if P and Q are both true, then P implies Q has to be true. Now, let's go down to the next line. Let's look at the case where P is true and Q is false. So that means you see me eat breakfast, and then you see me try to run 5 miles and I can't do it. What would you say about that green sentence? It's definitely a lie, correct? It's definitely false. I ate breakfast and then I could not run 5 miles. So the statement, if I eat breakfast, then I can run 5 miles, is clearly false. And that's where we get that second line from the truth table. Okay, now let's go down to the third line and let's explain that third line. Suppose P is false. What's that mean? It means I did not eat breakfast. Suppose Q is true. That means I can run 5 miles. Okay, this one's a little bit harder for some people to swallow. So look at the green sentence. If I ate breakfast, then I can run 5 miles. Instead of trying to show that that's true, let's instead show that it's not false. And then if it's not false, then it has to be true. Okay? So you see me get out of bed and not eat breakfast. And then you see me run 5 miles. Can you claim that that green sentence is a lie? The answer is no, you can't, right? Again, you might say, well, the sentence says that you have to eat breakfast in order to run 5 miles. And if you said that, you'd be wrong. The sentence does not say that. It never says that I need to eat breakfast to run 5 miles. Okay? Don't read into it something that's not there. The sentence only tells you a claim of what would happen if I did eat breakfast. It makes no claims at all about what will happen if I did not eat breakfast. It makes no claims at all about that situation. So you certainly can't say that that statement is false in a situation that the statement makes no claims about. Okay? So if P is false and Q is true, then that statement, if P then Q, cannot possibly be shown to be false. And if it's not false, then it is true. And the fourth line in the truth table has a very similar explanation. The fourth line says P and Q are both false. So what does that mean? Whoops. That means I did not eat breakfast and I can't run 5 miles. Is the sentence highlighted in green false in that case? No, for the exact same reason as the line right above it. The sentence highlighted in green only tells you a claim of what would happen if I did eat breakfast. So if I don't eat breakfast, then that green sentence has no bearing at all. Okay? And in that case, you certainly can't say that it's false. You would have no evidence to show that it's false. And if it's not false, then it has to be true. Okay? So that's where we get the lines of the truth table for a conditional statement. Please try to commit this truth table to memory, but that's not hard to do because of what I wrote in red there. The only time an implication is false is when the hypothesis is true and the conclusion's false. That's all you need to remember. In all other cases, it's true. Okay? Now, I want to look at a little bit more about conditionals here. So we've been talking about this. P implies Q. Okay? What about if you switch those and you write Q implies P? Okay? That has a name. It's also an implication, but what I want you to know this word is that is called the converse of P implies Q. And whether or not this is true has nothing to do with this being true. Okay, let's think about my car as an example again. I can say, if my car is out of gas, then it won't run. That's a true statement. Does that mean if my car won't run, then it's out of gas? Certainly not, because I can fill up my gas tank and still have my car not running, right? What if I take out the spark plugs? Then it won't run even with a full tank of gas. So what I want you to know is P implies Q is not at all the same thing as Q implies P. Their truth values do not have to be the same. Their relationship is called converse. They are converses of each other. Okay? Now, if you say not P implies not Q, that's called the inverse of P implies Q. And again, when two implications are inverses of each other, their truth values might be the same or they might be different. It's possible for one of them to be true and the other to be false. Okay? If you say not Q implies not P, that's called the contrapositive of P implies Q. So I would like you to know those three words. Converse, inverse, contrapositive. I want you to know those three relationships. Okay? I'm not going to show you today, but later on, very soon, I'm going to show you that contrapositives always have the same truth value. But converses and inverses don't always have the same truth value. But we'll do that in a couple of lectures, okay? All right, so that's a lot about what are called conditional statements. Now, there's something called a biconditional statement, which is this. What if you have P implies Q and Q implies P? So that means you have a conditional statement and also its inverse. That's called a biconditional because it's two conditional statements put together. Okay, and there's a single symbol that can accomplish all of that, and it is a double-headed double arrow like this. Okay, that's P implies Q and Q implies P. there's a way that we usually say that in the English language, which is we would say P if and only if Q. And that's abbreviated a lot of the times like this, P IFF Q. And what that means is this right here. It means P implies Q and Q implies P. Okay? So what would be an example of a biconditional? We might say, suppose that you're thinking of a number. Okay? A specific number. And suppose that P is the statement, the number I'm thinking of is even. And suppose Q is the statement, the number I'm thinking of is divisible by 2. Then the biconditional of those two would be this. The number I'm thinking of is even if and only if the number I'm thinking of is divisible by 2. Well, we don't have to repeat the number I'm thinking of. We can say it is divisible by 2. That's a biconditional statement. Okay? Is it true or false? Well, that's a whole nother question. This one happens to be a true biconditional statement, because that's the definition of the word even. The definition is divisible by 2. So it's true to say the number I'm thinking of is even if and only if it's divisible by 2. Even if I'm thinking of the number 3, in which case P would be false. But the statement P if and only if Q would still be a true statement. You would say 3 is even if and only if it's divisible by 2. That's a true statement. Even though P is not even, and even though 3 is not even, and 3 is also not divisible by 2. But the statement 3 is even if and only if it's divisible by 2 is still a true statement. Okay, let me show you the truth table for this. Here's what we're going to do. I'm going to put my variables P and Q. Okay. What are the possible combinations? You should be getting used to these 4 possibilities by now. Now, here's what I'm going to do. I'm not going to just tell you the truth values for P if and only if Q. What I'm going to do is we're going to figure it out, okay? Remember, P if and only if Q is just the conjunction of P implies Q with Q implies P. So let's review those two things. We did this in the last lecture. Let's make a column for P implies Q. And let's make a column for Q implies P. Oh, we didn't do this in the last lecture. We just did it earlier in this one. Okay, and then we will put those two together. I need to make my table bigger here. We will put those two together to get P if and only if Q. Okay, so let's fill in these two columns right here. What did we say about implications? We said the only time an implication is false is if the hypothesis is true and the conclusion is false. So the only time that should happen in this column is right here. P is true and Q is false. Then we're going to get P implies Q will be false. In all other cases, P implies Q is true. Okay, now let's do Q implies P. It's an implication, and I'm going to repeat myself. The only time an implication is false is if the hypothesis is true and the conclusion is false. Where is that here? The hypothesis is true and the conclusion is false. It's the third row. So that implication would be false. In all other rows, the implication is true. Okay. Now we can use those two columns to fill in this column, because that just means P implies Q and Q implies P. It's a conjunction, and in the previous lecture we talked about conjunctions. And what did we say about conjunctions? A conjunction is true only if both pieces are true, and it's false if either piece is false. So look at the first row. P implies Q is true. Q implies P is true. So in that case, their conjunction is true. Look at the fourth row. P implies Q is true. Q implies P is true. So their conjunction is true. Look at the second row. P implies Q is false, so automatically this conjunction of two things will be false. In the third row, Q implies P is false, so automatically this conjunction of two things will be false. So you need to know the relationship between P being true or false and Q being true or false, and under which combinations is P if and only if Q true or false. And it's actually very easy to see. Look, that's true if those are both true, and it's true if they're both false. So what does that mean? If P and Q have the same truth value, then their biconditional is true. Now look at this other two rows. The biconditional is false when P and Q have different truth values. So that's actually very easy to remember. Okay? A biconditional is true when both pieces have the same truth value. It doesn't matter if they're true or false. It only matters if they have the same truth value. Okay, and the biconditional is false otherwise. Okay, so very, very important. Conditionals and biconditionals. You need to know the relationships of when a biconditional or a conditional is true and when it's false. Okay? In the book, this covers sections 2.3 and 2.4. All right, have a good day.